Hello, I'm Igor Bellik, a professor in the Department of Mathematics at Georgia State University in Atlanta.
Uh, I'm Russell Jeter. I'm Igor's senior PhD student, graduating this spring. We're here to discuss foot force models of crowd dynamics on Wobbly Bridge, our upcoming paper in Science Advances. We would also like to discuss the impact of our work and what motivated us to research pedestrian models and footbridges.
So as outdoorsy people, we have come across plenty of footbridges that were suspect at best. And this naturally led us to investigating bouncing and swaying bridges. It turns out that the list of faulty bridges is very long, and many have experienced dramatic vibrations, and some have even fallen down. The first well-documented example of a faulty bridge was the Angers Bridge in France, which collapsed in 1850 when the French soldiers marched on it in step, leading to the bridge's collapse and the death of over 200 people.
More recent examples of faulty footbridges include the London Millennium Bridge, which began wobbling during the opening day festivities, the Clifton Suspension Bridge, which began wobbling in 2003 during the Bristol International Balloon Fiesta, and the Squibb Park Bridge in Brooklyn, which was closed in 2014 and just reopened this last April. The London Millennium Bridge incurred millions of dollars in repairs. The Clifton Suspension Bridge has to be closed to foot traffic during the Balloon Fiesta, and the Squibb Park Bridge caused both a lawsuit and costly repairs.
So the London Millennium Bridge incident attracted a lot of interest in the physics and engineering communities, but the interaction between walking pedestrians and the bridge has still not been fully understood. So to understand that, we need to find an adequate way to model a pedestrian walking mathematically. Well, and typically there are two extremes: simplified and elegant models that only capture the timing of your steps, and very detailed biomechanical models that can be unwieldy for modeling large crowds. And in our paper, we present a compromise between these two extremes: a simple yet biomechanically inspired model that allows us to simulate large crowds and predict the experimental data very well.
These pedestrian models can be used as crash test dummies when numerically probing a specific bridge design. This is particularly important because the US code for designing pedestrian bridges does not account for collective pedestrian behavior, but rather incorporates higher nominal static pedestrian loads and testing via periodic external forcing.
So and what we want to do is to better help engineers understand the role of pedestrians in the initial formulation of the bridge formula and avoid the range of dangerous frequencies, which cannot be identified through conventional linear calculations to eventually design robust bridges.
Thank you for watching, and please subscribe to our channel.
And watch your step.